Today's topic is the dot product of two vectors. So what's today's goal? By the end of today, after doing the note, looking at the homework, practicing, getting help, I want you to be able to recognize the need for the dot product and the situations when it's required. And then I want you to apply them using previously discussed methods. Okay? So you want to be able to identify when to use it, and then I want you to be able to use it. So how do I come up with a dot product? I start with an example. So we want to know the amount of work to move an object from point A to point B. So this is another physics concept. So I understand that some people don't see this right away. Physics people should be all over this. So I have two vectors in my diagram, F and vector AB. So F is the applied force. So this is you pulling a sled up a hill, pulling a cart up a hill. You're pulling something up a hill using a lever arm. So it could be a wagon, could be the rope from the sled. So this represents that handle. And you're pulling on it, so you're giving it some tension, so you're applying a force. AB is a displacement vector, so it's the distance from point A to B. So it has a magnitude, both have a magnitude and a direction. Work is force times displacement, okay? So that's from physics. So W equals force vector multiplied by your displacement vector, in this case AB. All right. So there is, and work is a scalar. So when you do work, okay, work is just a measurement of joules, of energy. Okay, so there's no direction to it. So that's the formula. So what we're going to do is we're going to take it and we're just going to come up with or develop our formula. So let's look at F. What I'm essentially going to do is I'm going to create an XY axis at that origin, except I'm going to turn or rotate the XY axis to match up with the slope. So our origin is here. This is now the new X and the Y axis there. So what is the force vector? And one of the things with work, force is only applied in the direction of motion. So the only force we're worried about here is the X component. All right, because if you're pulling upward, you're not moving it in the direction AB. So that would mean that for our diagram, our force would be the magnitude of the force, how hard you're pulling, multiplied by cos theta. All right, multiplied by the magnitude of the vector AB. So how far did you pull it? So we end up with a formula that looks like this. Cos theta. And because we're only dealing with magnitudes, when you're looking at magnitude of F, magnitude of AB, direction is no longer in this equation, and that's why it ends up being a scalar in the end. So in general, so I'll just put down here, in general, the notation here would be F, and it's called dot product because we use a dot to indicate that form of multiplication. And it's just going to be magnitude of F, magnitude of AB, cos theta. And what you're going to put on your formula sheet, because we're not using work every time, we're multiplying any two vectors together. This is the formula that you're going to put on the formula sheet for yourself. That's a scalar. Okay, so there's your dot product. Your dot product is one way, one process to multiply two vectors together, and it results, when you use the dot product, when you use this form of multiplication, it results in a scalar. Okay, so that's how the formula, how I developed the formula. I know it's not a theoretical approach, but I always like using it sort of from an application point of view. So you have this in front of you already, so I'm going to go through and talk about each one. Maybe I'll leave that screen up and bring it down. So some general notes. For non-zero vectors u and v, I'm going to add some vector notation in here. So these are vectors that are not zero vectors. We define the dot product as u dot v, and that's the formula that we just came up with on the previous slide. So there's our formula. Now, one thing I didn't mention on the previous slide is that the angle theta has to be an angle between 0 and 180 degrees. Why is that? Well, if we go back quickly here, and I'll use the magic pen, the angle between 0 and 180 degrees, that's an angle of 0. So that would mean you're pulling up the slope with all your force. If you were to pull in this direction, which would be at 90 degrees, you would be lifting lifting up the wagon straight up, so you're still moving the wagon. Here's 180 degrees. You're now pulling the wagon down the slope. If you go past that, you are somehow in the slope if you're pulling over 180 degrees. So you're inside the ground pulling downward, which doesn't happen. And when you pull down into the ground, or some people say, well, I'll just push, your wagon isn't moving. And in order for work to occur, there has to be a displacement. Okay, displacement cannot equal 0. All right, so displacement, or AB, can't equal 0 if we're going to have work. So going back there, that's all that's saying. The angle has to be between 0 and 180. If vector u or v is the 0 vector, then u dot v is 0. Okay, very, very important. If you look at it in terms of work, okay, force times AB, F dot AB. Does this make sense? Oops. AB equals 0. If your force is 0, that means you're not pushing. If you're not pushing, you're not going to move anything. So that makes sense. And I just said now, if you don't move an object, so if you push against a wall, you're not doing any work because the wall's not moving. So that makes sense that that's true. If theta is 90 degrees, okay, then cos theta, so the cos theta from this formula right here, cos theta is equal to 0. So if u and v are perpendicular, okay, perpendicular means they're at right angles to each other, the dot product is also 0. Okay, the dot product is 0, and again, that's because you're not moving in the direction the object's not moving in the direction of the force. So, all right. So two very, very key things here. So, and this is what needs to get on that cheat sheet and what you're practicing with. If two vectors, when you do the dot product, are 0, they are perpendicular. And this becomes really important for us in Unit 2. So here we're just learning about the dot product, but understanding and remembering this for Unit 2 is extremely important. Properties of the dot product, so these are just general properties that we'll roll through here quick. Number 1, I already talked about that. Okay, so this is one of the 5 properties. If u dot v is equal to 0, or the dot product is equal to 0, two vectors are perpendicular. Vectors u and v, they're commutative. So u dot v and v dot u are equal. So it doesn't matter the order when you do a dot product. Order does not matter. Okay? Order does not matter. It's like multiplying two numbers together. 2 times 3 is 6, 3 times 2 is 6. If you do the dot product of itself, you end up with the magnitude squared. So if you do u dot u, you end up with the magnitude of the vector squared. Okay? We'll talk about where that plays a role later on for us. Number 4, oops. For any vectors u and v with a scalar value, so that means we're going to multiply it by k. So if you look over here at the formula, the u vector is being multiplied by k as you do the dot product. All that means is that you're just doing u dot v and you're multiplying it by whatever scalar factor, or you can also put the k value with the v. So in the end, it ends up being k times bigger, whatever u dot v was going to be. And finally, for any vectors u, v, and w, all with vector symbols, u dot v plus w. So you can do the addition first, according to BEDMAS, do your brackets first. If you do v plus w, which will give you a vector, and do the dot product, it's the same as doing a distributive law, doing u dot v, so that's what I did there, u dot v, and u dot w. Okay, so the distributive law can be applied here. So rules for algebra that you're comfortable with or familiar with from grade 9 still continue on for us. All right, so those are the 5 properties that we're going to refer back to from time to time as we move through this particular unit.